Welcome to College Algebra, Module 1, Topic 1.1. This topic covers sets of numbers, order of operations, and scientific notation. In order to take a module quiz in this class, you must show a completed study guide for each video that you watch. If you have not printed off a study guide for Module 1, Topic 1.1, please do so now. Once you have your study guide, please follow along with the video, taking notes as you go. If you need to use additional paper, that's fine. Just attach those notes to the study guide. If you have any questions, please let us know. Objective 1, Sets of Numbers. We are going to talk about different sets of real numbers, beginning with natural numbers. These are the numbers 1, 2, 3, 4, and so on. These numbers are also called counting numbers. The next set of numbers are the set of whole numbers, which include 0, 1, 2, 3, and so on. The only difference between whole numbers and natural numbers is the number 0. The next set is the set of integers, which are the positive whole numbers, 1, 2, 3, and so on. The negative of the whole numbers, -1, -2, -3, and so on, and 0. The next set, rational numbers, are defined as the set of all numbers that can be written as P over Q, where P and Q are integers and Q does not equal 0. This means any number that can be written as a fraction of integers, where the denominator is not 0, is a rational number. The decimal representations of rational numbers either repeat or terminate. For example, 1/3 is a rational number. 1 is an integer, 3 is an integer, and as a decimal, that is 0.3 repeating. 1/4 is also a rational number, because 1 and 4 are both integers, or written as a decimal, 0.25 is a terminating decimal. The next set is the set of irrational numbers. These are any numbers whose decimal representation never repeats and never terminates. As a general rule, these are the really ugly numbers. The decimal numbers go on forever and ever. There's no repetition at all. In general, any square root of a non-perfect square is an irrational number, and any number involving pi, where pi is 3.1415, and it goes on and never ends and never repeats. So these are the two big types of irrational numbers. Another example is the number 0.010010001. It looks like it repeats, but there's no part of that number that goes on and on and on in the same pattern. The square root of 5, there's not a number that multiplied by itself will give you 5. That number is 2 point something something something. Therefore, because it can't be written as a rational number, it's an irrational number. The fourth root of 71. The fourth root means, is there a number that times itself 4 times will give us 71? There's not. Therefore, the fourth root of 71 is irrational. Pi, as I mentioned earlier, is always irrational. And E is a constant used in physics a lot. We'll talk about it later on in college algebra. But E is also an irrational number. All these sets that we've talked about make up real numbers. The set of numbers we get when we combine the rationals and the irrationals. Another way to remember real numbers are these are any numbers that can be graphed on a number line. In addition to graphing them on a number line, you can also think about these are any numbers that can have a value shown on a calculator. If you're interested in a picture, we've got the set of all real numbers up at the top. This includes most all numbers. Every real number is either going to be rational or it's going to be irrational. Just a note, a number cannot be both rational and irrational. If it's a decimal that ends or repeats, it's rational. If it's a decimal that does not end and repeat, it's irrational. The next layer down from rational is the set of integers, which is your positive and negative whole numbers. The next set under integers are your whole numbers, and then under that would be your natural numbers. So if you can find which set your number belongs to, then it's easy to identify the rest of them. For instance, 3 is a natural number. Well, it is also a whole number and an integer and a rational and a real. However, if we had a fraction, let's say 1/2, 1/2 is not a natural number nor a whole number. 1/2 is not an integer, but because 1/2 is a fraction of integers, it's a rational number, which means it's also a real number. For our purposes, all numbers are real except for a fraction with a denominator of 0 or an even root of a negative number, and we'll talk about that a little later. So let's begin with this example. Which of the numbers in the list above are natural numbers? Well, remember, natural numbers are the numbers 1, 2, 3, and so on. It does not include negatives, so the natural number would be 4, and it would also include 72. When we talk about whole numbers, that's basically natural numbers with the addition of 0. Because 0 is in our list, we need to include 0 in our list of whole numbers with 4 and 72. Integers are positive whole numbers, negative whole numbers, or 0. So we are going to include negative 27 in our list, 0, 4, and 72. The next set are the rational numbers. I'm going to skip rationals for a second and go to irrationals, because these irrationals are your ugly numbers. The square root of 40 is an ugly number. There's not a number times itself that would give us 40, so that one is going to be irrational, as well as pi, because pi is a decimal that never ends and never repeats. So that means all of the other numbers that are real numbers are also rational. So negative 27, negative 9 over 5, that's a fraction of integers. 0, 2/9, again, that's a nice fraction. 4, 6.5, and 72. Then, last question is, which of these are real numbers? Well, because we do not have any that have a denominator of 0 or the square root of a negative, then we can say that all numbers in this list are real numbers. Let's do another one. Which numbers in the list are natural numbers? Natural numbers are your nice counting numbers. Now this one's a little tricky. The square root of 9, well, the square root of 9 means what number times itself would give us 9? Well, 3 would. So because the square root of 9 is the same as 3, we must also include those in our natural numbers. So we have 1, the square root of 9, which is 3, and 8. The next number, whole numbers, we do not have 0 in our list. Now this is important because we've got the number 2 over 0. Well, 2 over 0 is a number that is undefined. That is not a real number, so we're just going to throw that one out. So our whole numbers are the same as our natural numbers in this case. Integers, we do have a negative 3, so our integers are going to be 1, negative 3, square root of 9, and 8. Rationals, again, I'm going to skip rational. Let's pull off the irrationals first. Irrationals are decimals that never end and never repeat. So we've got this number, negative 0.112123, never ends, never repeats. We do not have any other long numbers. We do not have any square roots that are not nice square roots. This time we've got negative pi. Well, because pi is irrational, negative pi will also be irrational. So our rational numbers are the numbers that can be written as a fraction of integers. So we've got negative 9/5, 1, negative 3, 7.123 because that's a decimal number that terminates, and 8. And then which of these are real numbers? Well, because we've got 2 over 0 in our list, which was undefined, which is not a real number, because we have 2 over 0 in our list that was undefined, we are going to say that our real numbers are all numbers in the list except for 2 over 0. Objective 2, order of operations. When an expression has more than one operation, you must follow the rules given by the order of operations to evaluate the expression. First step is parentheses, which also includes brackets, braces, and absolute value. Second, you do exponents. This will also include roots once we learn how to do radicals. Then we have multiplication and division, which means you multiply and divide in order from left to right. And then we have addition and subtraction, same thing. We perform these operations in order from left to right. When asked to round your answer to a specific place value, do this as the very last step, as sometimes rounding early on will cause your answer to be off just a little. Okay, evaluate the following expressions. For this one, we have 2 operations. We have an addition and a multiplication by the parentheses. Order of operations is we're going to do parentheses, exponents, multiplication and division, and addition and subtraction. Remember, this is please excuse my dear Aunt Sally. This is how some of you may have learned. Some of y'all have also learned PEMDAS, but that just tells you the order in which to perform your operations. There's parentheses, but there's nothing to do inside the parentheses. There are no exponents. We have a multiplication, so we're going to do that first. 6 times negative 2 would be negative 12. Then our last step is add and subtract. 4 plus a negative 12 would be negative 8. Let's try another one. This time we have parentheses, and we have something that we can do inside the parentheses. So in the parentheses step, 5 minus 9 is negative 4. So I'm just going to rewrite the rest of that problem. Exponents, well, we have negative 4 with an exponent of 2. This means negative 4 times negative 4, which is positive 16, minus 6, divided by negative 3. Then we do our multiplication and division. Well, in this case, we have a division. 6 divided by negative 3. So we get 16 minus 6 divided by negative 3 is negative 2. And then we've got add and subtract. So 16 minus a negative 2, which we could rewrite as 16 plus a positive 2, which would give us 18. Let's talk about rounding numbers real quick. To round a number, you mark the place value to which you're rounding. You look at the number to the right. If that number is 5 or more, you round up, which means you add 1 to the underlined place. Or if it's less than 5, then you round down, which means you don't change the underline. So just to give a couple of examples, if we had 1.3782 to the nearest tenth, that means we mark the tenth, we look to the number to the right, which is above 5, which means we're going to add 1 to the underlined digit, so the underlined digit would now be 1.4. If we wanted to do 201.6666 to the nearest hundredth, we mark the digit in the hundredth. Remember, you've got tenth in the first place, hundredth in the second place. So when you do that, you mark the 6 in the hundredth, you look at the 6 in the thousandth. Because it's 5 or more, you add 1 to the underlined place. So we would get 201.67. Last one, we'll just jump to the thousandth. you mark the digit that's in the thousandth spot. So we have tenths, hundredths, thousandths. So we're marking the 1. We're looking at the 9. That's above a 5, which means we add 1 to the underlined digit. So that would be 0.082. Just to fill in these others, you might want to hit pause and see if you can round the other ones accurately. Just to give you an example of one where we don't round up, the 0.0819 to the nearest hundredth, we would mark the digit in the hundredth spot, which would be the 8. This time we'd be looking at the 1. That's not above 5, so in that case we would round down, which means we leave that alone, so we would get 0.08. Okay, now let's talk about roots and radicals for a second. The square root of a number, denoted with a radical sign, or this little symbol right here, means to find the number that is multiplied by itself to give the radicand, or the number under the radical sign. For instance, the square root of 16, the radicand is 16. This means find the number that was squared that would give us 16. In this case, 4 squared is 16, so the square root of 16 is 4. Just to clarify, the square root of 16 is looking for a number that when multiplied by itself would give us 16. Well, we said just above that 4 squared is 16, but also negative 4 squared is 16. So why wouldn't the square root of 16 be negative 4? Well, in fact, the square root of 16 is really 4 or negative 4, but just to avoid confusion, what we decide to do is if we just say the square root of 16, that means the positive or the principal root. If we wanted the negative 4, then we put the negative out front, which would look like the negative square root of 16, in which case we would get the negative 4. The third root of 27, this little 3 out here is called the index. The 27 is called the radicand. What that means is what number to the third power will give us 27. 3 to the third is 27. So the third root of 27 is 3. Okay, let's do a few examples of roots and radicals. The square root of 49, what number multiplied by itself would give you 49? That would be 7. The square root of 121, what multiplied by itself will give us 121? That would be 11. Now the third root of negative 27. We said on the earlier page that the third root of 27 is 3. Well, the third root of negative 27 would be negative 3. We can do the third root of a negative since a negative to a third power is possible to give us a negative answer. Now let's make sure we know how to do our calculator, because sometimes these don't work out very nicely. Okay, I'm using a TI-83 Plus graphing calculator, which the keystrokes for the most part will be the same for the TI-84. So the square root of 13, there's not a square root on a button, but right above the x squared button is the square root button. So to get the square root of 13, we're going to go second square root of 13. Now notice when you did a square root, it opened the parentheses. So we need to close the parenthesis, and that would give us our answer of 3.60555. Our directions say round this to the nearest thousandth if necessary. Rounding to the nearest thousandth, tenth, hundredth, thousandth, you look beside it, it's 5 or more. So our answer would be 3.606 to the nearest thousandth. The square root of 50. So we are going to do the second square root of 50. close the parenthesis, and that would give us 7.071067812. Rounding that to the nearest thousandth, 7.071. Then the last one, the third root of 98. Notice we do not have a third root button on our calculator. So if we will look in this math menu, just touch the math button. Notice that option number 4 is the third root. We can either arrow down to option number 4, or we can just touch option number 4, and that would give us the third root. We want the third root of 98. Press enter, and the answer is 4.61043. Now when we round to the nearest thousandth, and we get 4.610 as an answer. Okay, this time we're going to evaluate, but we're going to round to the nearest hundredth. Hundredth is the second decimal place. So the fifth root of 131. Again, there's not a fifth root button. Okay, now we are asked to find the fifth root of 131. Notice there is not a fifth root button on the calculator. So what you do is you press the root first. So we're going to do number 5. Then we're going to go into the math menu, and option number 5 is the fifth root. So we can arrow down to where it says option 5, or we could have just selected number 5 to get the any root of 131. When we press enter, we get 2.65127,184. When we round this to the nearest hundredth, we get 2.65. This time we're going to evaluate the absolute value of pi to the third plus 1.2 to the second power. So to clear our calculator, now absolute value, we're going to go into our math menu again. This time we're going to slide over to the right to where it says number up at the top. So we're going to right arrow to number, and the absolute value is number 1. So we're going to press absolute value. Now pi is on your calculator, and it's right above the up arrow under the clear button. So we're going to do, okay, the pi button is right above the up arrow, but it's in yellow. So we're going to go second pi. Now we need a power of third, so I'm going to do to the power of 3 plus 1.2 to the power of 2, or we can just use the square button instead of doing the up arrow 2. Press enter to get an answer, and we get 32.44627,668 rounded to the nearest hundredth would give us 32.45. And then the last one, now this is a fraction, and fractions are a little tricky. What you've got to do is you've got to tell the calculator that we need to do what's in the numerator first and then what's in the denominator. So we're going to use parentheses to separate the two. So I'm going to clear my calculator, open the parentheses for the top, 1 plus the square root, remember that is second square, of 2. We're going to close the parenthesis for the square root, and then we're going to close the parenthesis for the top of the fraction. Divided by, and then the denominator of the fraction, because it has more than one term, we've got to put it in parentheses. So we would get 3.7 minus 9.8. And then when we press enter, we get negative 0.3957727,151 rounded to the nearest hundredth. We mark the 9, we look beside it which says we add 1. Well, if you add 1 to 9 you get 10, so in this case it's going to be negative 0.40. Objective 3, scientific notation. Scientific notation is a way we write extremely large or extremely small numbers without so many zeros. It involves writing a number as a product of a number between 1 and 10 times a power of 10. That is, a times 10 to the n, where a is between 1 and 10 and n is an integer. For example, the number 6,100,000 would be written in scientific notation as the product of a number between 1 and 10. So in order to get that as a number between 1 and 10, we're going to move the decimal right between the 6 and the 1. So it's one number, the decimal, and then the rest of the numbers, times 10 to a power. Now the power of 10 is the number of places that the decimal actually moved. Well, the decimal was here, so we move it 1, 2, 3, 4, 5, 6. We're moving it 6 places. Our power would be 6. So we would get 6.1 times 10 to the 6th power. A couple of notes about scientific notation. The first number has one digit to the left of the decimal. The power of 10 is equal to the number of places the decimal actually moved. A large number, meaning larger than 10, has a positive exponent. A small number, smaller than 1, has a negative exponent. So when we write 0.000423 in scientific notation, we figure out where the decimal goes, so it goes right after the first non-zero number, which would give us 4.23 times 10 to a power. Well, how many places did we move the decimal? 1, 2, 3, 4. But because this is a really small number, it's a decimal number less than 1, then we show that by having an exponent of -4. Let's do a few more examples. The distance to the sun is 9.3 times 10 to the 7th miles. To write this number in standard form, observe a couple of things. The power of 7 means we're going to move the decimal 7 places, and because it's a positive exponent, we're going to make the number large, which means we're going to have to move the decimal to the right. So that would be 9.3, moving it 7 places. One place gets it beyond the 3. Then we would still need 6 more places, which means we're going to have to add 6 more zeros to get our 7 places. So we would have the number 93 million in standard form. Weight of kilograms of an electron is 9.11 times 10 to the -31st power. Now to write this number in standard form, notice we've got 9.11. The 31 means we're going to move the decimal 31 places. The negative means it's a really small number, so we're going to have to move the decimal back to the left to make it a smaller number, but we're going to move it 31 places. One place gets it past the 9, which means we are going to need 30 zeros. Wow, that's a lot of zeros. Imagine putting that one in your calculator. Okay, now we're ready to evaluate some expressions to where we're performing operations on scientific notation. So first we're going to multiply these and leave our answer in scientific notation. I always think it helps on these to think of this as 2 times 10 to the 6th times 6 times 10 to the -9th. So rearranging the multiplication, we've got 2 times 6, which would give us 12. And then we've got 10 to the 6th times 10 to the 9th. If you'll remember from intermediate algebra, to multiply powers of 10s, you keep the base of 10 and you add the exponents. So 6 plus -9 would give us -3. Now, That looks good, but that's really not scientific notation because this first number is not written between 1 and 10. So to convert it to scientific notation, we're going to rewrite the 12 as 1.2 times 10 to the 1. Now, times the 10 to the negative 3 that we already have, we would get 1.2 times 10 to the power of, remember, add your exponents. 1 plus negative 3 would give us negative 2. Now in standard notation, this means the power is 2, which means we're going to move it 2 places. It's a negative 2, which means we're going to make it smaller. So that would be 0.012. Same thing for division. 1.2 times 10 to the 4th divided by 3 times 10 to the negative 8. We're going to divide the numbers first. 1.2 divided by 3, that would give us 0.4. Now divide the powers of tens. 10 to the 4 divided by 10 to the negative 8th. When you're dividing like bases, you subtract your exponents. We would get 4 minus a negative 8, or 4 plus a positive 8, which would give us times 10 to the 12th. Same thing. This number is not in scientific notation because 0.4 is not between 1 and 10. So 0.4 can be rewritten as 4 times 10 to the negative 1 times the 10 to the 12 that we already have, which would give us 4 times 10 to the 11th power. In standard form, that means we're going to move the decimal 11 places to make it a large number, which means it's a 4 with 11 zeros, which would give us 400 billion. Now let's look at these on your calculator. This is a great check. Okay, we're going to enter this just like it's shown. So we're going to do parentheses 2 times 10 to the power of 6. Close that parenthesis, times, then in the next set of parentheses, 6 times 10 to the power of negative 9. When we do it, that gives us standard form, which is our 0.012. To get it in scientific notation, if you'll press your mode button, you notice up on the top row it's flashing normal. Well, if you arrow to the right, that is your scientific. So what we do is we press enter, and now the scientific is highlighted. So I'm going to press clear to get us back to our other screen. Now when we press enter, that gives us our scientific notation, which is 1.2 times 10 to the negative 2. Now notice your calculator says E. That just means times 10 to the power of negative 2. Last one of these. So in order to do the division, first thing you need to remember is you need to put your parentheses on there. Otherwise it throws all of your order of operations off. So we would have in parentheses 1.2 times 10 to the power of 4 divided by, oh, don't forget to close that parenthesis, divided by, then in parentheses 3 times 10 to the power of negative 8. Then when we close that parenthesis, we get 4e11, which means 4 times 10 to the 11th power. In standard notation, remember this is 4 with 11 zeros, just like we did on the previous page. Objective 4 is applications. The first application we're going to do is the percent change formula. Sometimes it's necessary to find the amount of increase or decrease in terms of the original value. If a value changes from A to a new value B, then the percent change is given by B minus A divided by A times 100. Occasionally you'll see this as percentages, and it'll be P2 minus P1 divided by P1, and then you multiply it by 100 to write it as a percent. In basic math, we used to teach this as the amount of increase or decrease divided by the original, which is exactly what we've got here. A is the original. You subtract A from B to get the amount of increase or decrease, and then you multiply it by 100 to write it as a percent. So here's our example. From 1985 to 2002, the average tuition and fees at private colleges and universities rose from $6,121 to $18,273. What was the percent change? Well, it's the amount of increase, which would be your second value, subtract your first value. So your amount of increase or decrease is $12,152 divided by the original, which was the $6,121, is 1.9852 times 100 to write it as a percent, which gives us 198.529652. Notice this problem says round to 2 decimal places. So the 2 decimal places would be hundredth, which would give us 198.53%. So that is an increase of almost 200%. Another example. Sam earns $12 an hour by lifeguarding at the pool. He gets paid double time for any hours he works over 40 per week. He gets time and a half for hours worked on Sunday. How much will Sam earn this week if he works 44 hours during the week and 6 hours on Sunday? So we need to do a couple of things. Sam has 3 different pay scales. His regular pay is $12 an hour for the first 40 hours. He gets paid double time for any hours worked over 40. So this is what we're going to call overtime hours. So double time means 2 times his regular, so overtime hours, Sam is making $24 an hour. And then Sunday, he gets time and a half. Well, time and a half means we're going to multiply 1.5 times 12, which would give us 18. Or we could have just said, well, time is $12 an hour. Half of that would be 6, so 12 plus 6 is 18. So when Sam is calculating his paycheck, he's got regular hours, which would be 40. He's got overtime hours, which would be 4, because he worked 44 total hours. And then he's got Sunday hours, which was 6. We have 40 hours times $12 per hour plus 4 hours times $24 per hour plus 6 hours times $18 per hour, which would give Sam a total of $684. You are now ready to do the homework for Module 1, Topic 1.1 in My Math Lab. As always, if you have any questions, let us know.